Right, so I'm the last person standing between you and some bagels, but fortunately this is a talk about some topology. So you will see a bagel before you actually eat a bagel. So this, thank you for the invitation, and it's a pleasure to talk about topology to a community of people who work on dynamic systems and machine learning, because there's been a lot of interaction between these fields recently with topological data analysis. And today I'm going to focus about whether the time series data that you collect actually explores the fundamental topology of a manifold, and I'll quantify what that means. So just to give some context about what I work on, what my field is, it's called TDA, topological data analysis. And usually sort of our pipeline is that we want to give some insight into the shape of data. So we start with some data that could be some point cloud. It could be some combinatorial data, such as a graph. It could be some literal complex, just something with a triangulation, or cell complexes. And we want to measure topology, right? So what does it mean to measure topology algebraically is to measure cycles, measure loops, measure voids and holes, and so on. So we usually go from our raw data to some intermediate object, and then we use that intermediate object to compute some invariance, some algebraic or geometric invariance. So in this case, it's persistent homology, but today I'm not going to talk about that. But this is usually the pipeline. And we'll follow this pipeline today, but with slightly different tools than the standard regular usage. So there's our bagel. Since this is a dynamic systems conference, we'll be focusing on time series data. And so I think every talk I've seen, everything works in Euclidean space, right? But what if your topology, what if your time series or dynamics is on some manifold that is not Euclidean? For example, it might be on a torus. So you might think, when do I have a dynamic system on torus? Well, it's just a product of S1s. And we've seen, I think 2 talks ago, the Kuramoto oscillator. That's a bunch of oscillators, and it forms an N torus. So that's a very simple example of how dynamic systems can occur in spaces with non-trivial topology. But I mean, okay, torus, it's kind of a boring space. I mean, what's more interesting is a Klein bottle. If you haven't seen a Klein bottle before, so you take a sheet of paper like that. So you glue the 2 sides to form a cylinder, and then you glue the top and bottom with a twist, like this. So you can't actually embed that manifold in R3. You need R4 to do that. But if you tried your darnest best to stick into R3, this is what a Klein bottle looks like. And we're going to look at some dynamic system on Klein bottle. So we have some vector field in this example on a Klein bottle. And with a sampled path. So the color is the time. So I think my time series starts somewhere here. And then it goes across this edge. Since that edge is glued to that edge, it comes out here. And eventually, so as you see for the yellow bits, it's the long time, right? So it settles onto a limit cycle on this Klein bottle. Okay, great. So the question is, well, does that limit cycle orbit around some non-trivial loop of our space? How do we quantify that? And since we're working with data, how can we actually go from this sampled path to that topological information? How do we go from the discrete data to the actual underlying loop itself? So, said I'm in TDA, so this talk will be divided into 3 bits, the T, D, and A. So T, I'll talk about the algebraic machinery, the topology that allows us to derive insights. And the main character in this is called monodromy. So what it basically is I have a path in some space, and I attach some algebraic data to that path. And that's going to remember something about the topology. The second part is how we're going to bring that algebraic stuff, topological stuff, and interface it with some real data that requires some geometry. And the third part is the analysis. Now we're going to show how to do the analysis on the system I've just shown on a Klein bottle. So let's jump straight into the algebra. So how do we classically measure loops in our space? So we use something called the fundamental group. So we want to record loops in space that is equivalent up to continuous deformation. So those form classes of loops in space, and since we could compose loops to form new loops, they form a group. And here are some sample spaces. So what is the fundamental group of S1? Well, how do you characterize loops on a circle? Well, it's just how many times you turn around the circle. That group is just integers. And if you go the other way, you go you take the minus sign. So it's just a group of integers. What's a torus is two circles taken as a product. So you have a product of two integers. And the Klein bottle, well, that's the tricky one. So it's almost like the torus, but it's not got the same product. It's a twist. Those two cycles have a twist. So hence, not your usual direct product, but what's called a semi-direct product. I won't go into what that is, but if I abelianize those groups, so I allow the orders to be mixed, you see that the semi-direct product does not abelianize the same thing as the direct product. So you get a integer and direct sum with an odd and even Z2 group. So there's some very beautiful classical algebraic topology. So turns out you could relate cycles on the space, loops on the space, with symmetries of some lifted space. So if M is our space, I have what's called a universal covering space, M tilde. And basically, you can relate the cycles and the loops on M with symmetries of the lifted space above M tilde, the covering space. So as an example, we have this staircase outside. So what this demonstrates is the universal covering of S1. So you take the real line, and you model it out by integers. So what's this? What's this map that models out by integers? It's the exponential 2 pi it, right? So you have this symmetry of translation by integers. You model that symmetry. You get a circle. So, and everything we're going to do is we're going to simplify everything in this talk and work with this lifted space. So does this exist for any space? Not really, but for most cases you care about with nice enough topology, such as manifolds, you do have a unique universal covering manifold. And what's special about it? It's simply connected. So any loops downstairs is generated solely by the symmetries on that covering space. There's no loop upstairs being inherited downstairs. And we have that group action, which is a symmetry. And what is that group? That group is exactly the group of loops. There's an isomorphism, and we'll get into this isomorphism. That's the monodromy. As we've seen, an example is covering of S1, which is quotient of the Z action, integer action on the real line. So it exists for many model spaces, compact surfaces, your tori, your servers of the genus, whatever, Klein bottles, make the groups. So you could have special orthogonal groups, and it's covered by a spin group. SO3 is double covered by SU2. But basically, if you triangulate your space, you could really construct your covering space. So this is this is some classical thing we could generate and compute very well. Oh, did promise a few examples on the board. Since we'll be working with, let's go back to torus. So, the universal covering of a torus space is R2. You have a grid. You chop up your grid in R2 into integer grid. You have your two integer actions on your R2, you quotient by that action, and you get your torus, which becomes the square with those sides identified. What about the Klein bottle? Well, last night I was quite jet lagged, so I woke up at 4 a.m. in my hotel room. So I stared at my ceiling and thought, well, actually, since I'm talking about the Klein bottle, I should actually give you an example of where you could see a Klein bottle in the dynamic system in the real world, right? So here's an example. So the Klein bottle, you get the universal covering space as R2, but it factors through a torus. So you impose an extra symmetry on torus, a Z2 symmetry, which I won't go into, and you quotient that, and you get a Klein bottle. It's a twisted torus. And how do you get that twist? So I was quite pleased. So let's think of a dynamic system that lives on a torus. So let's take a rod and put a flag on it. I give it 2 degrees of freedom. So a torus, it has 2 cycles. So I could rotate the flag in this way. But I could also have this axis rotation out of plane. So that's my 2 angles of my torus, my 2 S1s taken as a product. And if I want to construct, that's two symmetries, right? That gives you a torus. So I want some extra symmetry on my torus to give me something that lives in a Klein bottle. So what I do is I add another flag here. So these are 2 coupled flags. And if I rotated the flag by theta 1 this way counterclockwise, I have rotated the other flag the other way. There's 2 coupled flags. And so you could sort of look at the symmetries of the system and show that the dynamics of that system lives on a Klein bottle. So this whole stuff about topology is not completely abstract. I could give you a dynamic system that engineers would use. Maybe, you could see this in your car, maybe, right? Coupled things joined together, right? Things rotating around each other. That lives on a Klein bottle. So this is not completely academic. So there you go. So you go from a torus, you have that extra symmetry, and you get a Klein bottle. So we're going to work with this lifted covering space. And we're going to classify powers using that. So we mentioned the monodromy. So it turns out if you have a loop in your original space, it actually lifts and winds to a loop in your covering space. So for example, if you walk around your spiral staircase, you're going around S1, but you're lifting your path along up your spiral staircase onto R. So you go around, do I have another color? Yes. You go around your circle, but actually you're going up stairs. You're going up your real line. So your paths, your loops lift up to this covering space. And these loops unwind when you lift, if and only if they are non-trivial. So this lifting procedure completely characterizes your cycles. And in many cases, we really want that, right? Because why work with a Klein bottle when you could work with Euclidean space? No? You can lift your paths up on your Klein bottle up to your Euclidean space. That's the space we're going to work with. And the monodromy simply measures how this loop unwinds. There's some algebraic data that measures how this loop unwinds. And returns a symmetry that generates the loop in question. So I'm not going to perhaps go into that. And this lift is unique up to homotopy. So if you have a homotopy class of loops that's uniquely defined up to continuous deformation, you lift to another class of loops that's uniquely defined up to deformation upstairs. So, okay, we've boiled down the issue of looking at loops to looking at lifts and computing this algebraic thing called monodromy. Without going into too many details, this I would have described as monodromy for loops, but you could also do monodromy for paths. In that case, you're not working with fundamental group. That's something that's slightly scary called fundamental groupoid. But the point is, this monodromy thing respects composition. You could sort of compute this monodromy along a path. You could split the path into two. And then you could compute a monodromy on the subpaths and then take the product of those monodromies, and you get the monodromy of your entire path. So you could adopt a divide and conquer technique to these monodromy things. And this will be important. So there's an assignment of group elements to paths respecting composition. So that's a lot of topology for a dynamic systems conference. Some people have already left for the bagels. But let's have a brief recap. So we've said that, okay, rather than looking at our original space, we want to work with our lifted space, our covering space, which is much simpler to deal with. And we have this algebraic gadget that we want to compute called monodromy. And inferring the class of loop is the same thing as computing lifts. But how do we do that on data? This is a machine learning conference after all. So here's how we do it. So what do we mean by sampled paths? So let's say we have gamma, our path in space M, and we have some finite observations along the path at times t0 to tn. So there's an ordered sequence of observations. And we assume that it's a dense enough set of observations, meaning, let's say, roughly speaking, if you take the injectivity radius of a manifold, it's smaller than that. And your path is contained within an injectivity radius ball of away from a geodesic path connecting those 2 points. So the point is, we want to use the minimizing geodesic between those points as a topological surrogate for those paths. And if you sample dense enough, we can. Why do you want to do that? Because, well, monodromy, we actually only care about endpoints of lifts of paths. And then if we choose geodesics, minimizing geodesics, we're actually just only using metric information. So if you know the metric upstairs, R2, we all know about the metric, how to compute distances on R2, you could compute monodromy. So I'm perhaps not going to go through all the details of this, but basically, by using this procedure, you could use the metric upstairs to help compute your algebraic information downstairs. And that is if you could approximate a path using piecewise geodesics. So just to explain what this means, so we have a bunch of points on my Klein bottle. We lift the points of my Klein bottle to the covering space. Geodesics lift to geodesics, minimizing geodesics, lift to minimizing geodesics. So geodesics on my Klein bottle lift to geodesics in Euclidean space. And by querying these geodesics upstairs, I could record the monodromy. Yeah, I'm assuming it's an isometry, yes. So those universe covering spaces, you can make them an isometry, yes. So let's go back to our actual sampled path. So we have our finite observations. What we do is we compute on small bits of a path using a piecewise geodesic approximation, the monodromy. And then because monodromy integrates, you could piece them together to get the whole thing. We just integrate it along the small paths. So another intermission. So what we've done, so we've answered our 2 questions. How does our time series / time system wrap around this manifold? How can we quantify this? We look at the monodromy of the fundamental group. How can we reconstruct this from finite data? We use this lift to the covering space and use the metric information on upstairs. And it's very appropriate to point out that we do need that covering map to be an isometry. So just a demonstration. So here is my sample path again, and this is my monodromy integrated. So what is the group of the fundamental group of the Klein bottle? That is a group of loops. It is the semi-direct product of 2 integers. So I could represent each group element as a pair of integers. So that's what I'm plotting here. So as I go along this path, I accumulate these group elements. I just multiply them. And I travel through this space of group elements. And you could see that, initially it doesn't converge to your limiting cycle, but then when it converges to a limiting cycle, it does do this oscillation in the space of your group elements. So what we then do is, okay, I pick a point on my limit cycle, and I measure the distance of each point along the path to that point. So as I go around limit cycle, I come back to the same point again, so I get these values, right? So if distance is 0, I come back to the same point again, that means it completes a loop. So I take that chunk of my path and I compute the monodromy of that path. So I'm going to probably skip this because it's just some algebraic bookkeeping, but we actually want to look at conjugacy classes of dependent vector group. But we can actually ID our limit cycle. So here are 4 different dynamic systems on my Klein bottle. And for the first one, this is all computed on real data. This is not synthetic, it is not academic at all. I literally wrote down some random vector field. I ran my ODE solver and get a trajectory, and I put through machinery and computed these numbers, right? So the numbers above classify as a topological classification and ID for what these limit cycles wrap around. So maybe the most trivial one is the one if a limit cycle just goes around a loop that's contractible, right? So this one. So I start somewhere here and then end up just orbiting over there. That is a contractible loop. So my ID gives me, that is a trivial loop, 0, 0. It's an identity. Then you see this limit cycle, which basically goes from the top down to the bottom. It sits in the 1 - 1 conjugacy class. You get another one. It goes down and up again. That's 0, 2. And this kind of wraps around diagonally across those 2 edges. So we can go from the data to the topology of these limit cycles. So, well, I raced through that. I'm in my summary slide. So, so what have we learned today? So if you didn't really sort of want to think about topology, this is maybe just a very simplified summary of what I've just said. So we went from time series data, and we want to look at loops in your time series and whether they wrap around non-trivial topology of the underlying space, such as the Klein bottle or the torus. And we've presented a means to go from the data to an actual ID of that limit cycle that classifies that according to the topology of the underlying manifold. And we do that by using this technology in algebraic topology called universal covering spaces. Basically, we work with lifting these paths up to a space where topology is simpler. And we could think of things in terms of symmetries. And if there are people in the audience who are interested in further questions, this leads on to an TDA. So this whole thing about a path, right? So really it's just, I have a path graph and a map of this path graph into some manifold. That's what we've been discussing, right? And then these vertices map onto points on my manifold. So it contains a map from the geometric realization of the path graph to manifold. So what about other graphs? What about simplicial complexes? Can we use this to understand that? The answer is yes. And you could use the same technology to answer this question. So if I give you a graph, let's say a simplicial complex, and I say, okay, the vertices must map to these points on my manifold, is there a continuous map from this graph or complex to that manifold? And you could use this machinery to answer those questions. So if you could compute the universal covering of the manifold, you could say yes or no. And the way to do that is you just query the triangles of your complex. You say, okay, if the monodromy around that triangle is trivial, then you could embed a two simplex that sticks onto that triangle and map it onto your manifold. So this technology can answer sort of questions outside of perhaps dynamical systems and in the broader TDA world. So thank you for your attention, and I'll stop here.